Hello, my name is Jacob Milham, and this project is called Pitch Recognition to Plate Approach, Modeling Swing Decisions from StatCast Data. For this project, I wanted to study a part of the baseball decision making that often gets discussed but is not always modeled directly, the swing decision itself. Rather than focusing only on outcomes like hits, whiffs, or slugging percentage, I wanted to see whether pitch level data could help explain when hitters choose to swing and when they choose to take. The bigger goal was to build something that starts with prediction but ends with baseball insight. In other words, can we move from raw StatCast data to a predictive model to visuals and scouting information that can actually help us understand hitter behavior and pitcher attack patterns? The motivation for this project comes from the fact that every pitcher forces a hitter to make a rapid recognition decision. In a very short amount of time, the batter has to process location, count, pitch type, speed, movement, and timing, and then decide whether to attack the pitch. A lot of baseball analysis focuses on what happens after that decision, such as contact quality, strikeouts, or run value. But the decision itself is a meaningful part of plate approach and pitch recognition. I believe that pitching development has made leaps and bounds with the prevalence of StatCast, Hawkeye, and Edgertronic systems, just to name a few. The next frontier in baseball is catching batters up. If we can model swing behavior directly, then we can start to understand not just what happened, but why a hitter behaved the way he did. That is why this project focuses on swing behavior as its own analytical target. The core research question for this project was how well can pitch level features such as location, count, pitch type, velocity, movement, and handedness predict hitter swing decisions, and how can those predictions be used to support baseball scouting and approach analysis? That question I broke down into two parts. The first part is predictive. How well can pitch level StatCast features predict swing versus take decisions? The second part is interpretive. If that model works, can those predictions be translated into interpretable visuals and applied scouting insight? So the project was not just about getting a strong classification score, also about showing that those predictions can become a bridge between technical modeling and baseball application. To answer that question, I used pitch level StatCast data pulled in Python with PyBaseball. The project window ran from May 1st, 2025 through June 28th, 2025, and the initial data set contained 229,216 pitches. Each row represented one individual pitch, which made the pitch the natural unit of analysis. I worked with this 2 months of data to be a manageable starting point, with the future goal to build upon this further. The core features I kept were the ones most likely to influence hitter decision making. Those included horizontal and vertical pitch location, the count, pitch type, velocity, movement, and batter and pitcher handedness. This gave me a large pitch level dataset with both physical pitch characteristics and game context variables, which made it a strong foundation for modeling swing behavior. After pulling the raw StatCast data, the next step was preparing it for modeling. First, I converted the key pitch and count fields into numeric format and removed duplicate pitch records. Then I created a series of pitch level labels that made the data much more useful analytically. The most important labels were did swing and did take, which defined the binary classification target. I also labeled outcomes such as is whiff, is in play, and made contact so I could preserve more detail about how that pitch ended. Then I created strike zone and decision flags, including in zone, zone swing, zone take, chase, and take ball. These helper columns were important because they allowed me to move beyond pitch outcomes and describe pitch decisions in context. The overall goal of this step was to turn raw StatCast data into a clean pitch level decision dataset that was ready for modeling. The final model performed well. The ROC-OC was 0.885, which means the model showed strong ability to distinguish swing pitches from take pitches. In practical terms, that means that the model was very good at assigning higher swing probabilities to actual swing pitches than to actual take pitches. The model's overall accuracy was 0.80, and the performance was balanced across both classes. Recall was 0.78 for takes and 0.81 for swings, with F1 scores of 0.80 for takes and 0.79 for swings. The confusion matrix also showed that this model was getting most decisions correct, with 18,551 correctly identified takes and 17,770 correctly identified swings in the test set. Why does that matter? Because these results suggest that pitch location, count, movement, and handedness carry a real predictive signal for hitter decision making. That gave me confidence that the model was strong enough to support the next phase of the project, which was turning these predictions into interpretable baseball visuals. A key point in this project is that the model output matters not just because it predicts swings correctly, but because it produces probabilities. A simple yes or no prediction is useful, but predicted swing probability is much more informative. It lets us ask where the model expects swings to happen and how actual hitter behavior compares to those expectations. That is important because baseball decisions are rarely black and white. What makes a model valuable in this setting is not only whether it guesses correctly, but whether it produces a realistic decision surface that can be visualized and interpreted. So, this next slide is really the bridge from the technical modeling step into the baseball interpretation step. Once the probabilities were generated, I could aggregate them by pitch location and compare actual swing behavior to model expected behavior. That is where the project stopped being only a classification exercise and became an approach analysis tool. So this slide shows the three main decision heat maps created from the model output. The first map shows actual swing rate by location. The second shows the model's predicted swing probability by location. The third shows the difference between actual and predicted behavior, or actual swing rate minus predicted swing probability. The first key finding is that the actual and predicted maps align pretty closely. In both, the highest swing activity was centered in and around the heart of the strike zone, which is exactly what we would expect from real hitter behavior. That matters because it shows the model learned a realistic spatial pattern rather than random noise. The third map, the difference map, is especially valuable. It highlights where hitters swing more aggressively or more passively than the model would expect. In other words, it starts to isolate zones where behavior deviates from the learned baseline. That kind of map can matter for player development, scouting, or approach analysis because it helps identify where decision making is aligned with expectation and where it is not. So the technical route here was straightforward but powerful. Predict swing probability at the pitch level, bin those predictions into a strike zone grid, and then compare actual behavior to expectation. The result is a visual framework that can support baseball interpretation. To show the framework could be applied in a practical baseball context, I built a focused scouting example around Tarek Skubal against right-handed batters. This step mattered because it demonstrated that the project could move from general swing modeling into actual baseball scouting. Instead of stopping at league-wide or full sample behavior, I wanted to show that the same workflow could be used to understand how a specific pitcher attacks a particular side of the plate. For this case study, I isolated 757 pitches thrown by Skubal to right-handed batters during the same project window. Then I summarized three things: his overall pitch mix, his pitch mix by count bucket, and the location patterns of his top pitches. So this slide marks the shift from model validation into a practical use case. Against right-handed batters in this sample, the changeup was his most used pitch at 31.6%. That was followed by the four-seam fastball at 27.1% and the sinker at 25.9%. That alone is interesting because many people would assume the fastball leads that mix, but in this stretch, it was the changeup. The count bucket split made the pattern even clearer. In even counts and hitter ahead counts, Skubal leaned more heavily on the sinker, but once he got ahead, and especially with two strikes, the changeup became his primary weapon. In two strike counts, he threw the changeup nearly 42% of the time, compared with about 34% for the four seam. The location heat maps also suggested a strong vertical pairing. The four seam generally occupied a higher band, while the changeup clustered lower. That kind of vertical separation is important because it can make both pitches play up against right-handed hitters. Why does this matter? Because it shows that the framework can produce a real scouting insight, not just a statistical summary. In this case, it revealed that Skubal's changeup was the defining pitch in his right-handed hitter attack plan, especially in finish counts. So the project successfully moved from modeling swing behavior to generating a pitcher-specific scouting conclusion. The value of this project is that it models hitter behavior directly rather than focusing only on final results. At a technical level, it shows that pitch level StatCast data carries strong signal for swing decisions. At a baseball level, it creates a framework for turning those predictions into interpretable visuals and applied scouting tools. That matters because swing behavior sits at the intersection of both pitch recognition, plate approach, and pitcher attack strategy. If we can model that behavior effectively, then we can better understand how hitters respond to different pitch contexts and how pitchers exploit those tendencies. This framework could eventually support player development, pregame scouting, and matchup preparation. It helps bridge a gap between analytics and practical baseball communication by taking the model output and translating it into charts, heat maps, and scouting style conclusions. So the project's significance is not just that it built a classifier, it is showed how a classifier can become part of a baseball decision support workflow. Before wrapping up, it's important to briefly talk about the limitations of the project and what future work could look like. First, this project was completed within the limited time window of the class. Because of that constraint, the goal was to build a functional and interpretable modeling pipeline rather than a fully production ready decision system. The workflow demonstrates how swing decisions can be modeled, but there are several ways that analysis could be expanded. One limitation is that the project does not yet include a full expected value framework for swing versus take decisions. Right now, the model focuses on predicting the probability that a hitter will swing at a given pitch. A natural next step would be to pair those probabilities with run value or expected value calculations so that each decision could be evaluated in terms of its actual impact on run production. Another limitation is that the final output does not yet produce hitter specific matchup cards. The model can already evaluate individual pitches in context, but the presentation layer could be expanded to generate reports tailored to specific hitters facing specific pitchers. Additionally, pitch sequencing effects were only partially captured through variables like count and pitch context. In reality, hitters respond strongly to pitch sequences and patterns across an at-bat. A more advanced version of this model could incorporate sequencing features directly, which would likely improve predictive power. Looking ahead, there are several exciting next steps this could take. One would be building hitter-specific matchup reports using the model's predictions. Another would be incorporating the run value into swing and take decisions. And finally, the entire workflow could be turned into an interactive dashboard that would allow analysts, coaches, or players to explore matchup information, pitch tendencies, and swing decision probabilities in real time. These improvements would move the project from a modeling demonstration like it is here toward a practical decision support tool for baseball analysis. In conclusion, this project showed that swing behavior can be modeled effectively from pitch level StatCast data. The model produced strong predictive performance. More importantly, the model output could be translated into interpretable decision maps that showed where hitters behaved as expected and where their behavior deviated from those expectations. The project also showed that this framework could support applied baseball analysis. The Tariq Skubal case study demonstrated how the same pipeline can be used to create a practical scouting report and identify a clear attack pattern against right-handed hitters. There are still important next steps. The project used the limited time window and it focused on swing decisions rather than a full expected value framework. Future work could extend this into hitter-specific cards, incorporate run value, model pitch sequencing more directly, or package the workflow into an interactive dashboard. But as a final project, this work answered the main question successfully. Pitch level data can be used not only to predict swing decisions, but also to produce interpretable and useful baseball insight. Thank you.